So this is the title of the talk. So let me begin by giving a general idea of what soft graviton theorem is all about. So we will consider any general coordinate invariant quantum field theory of gravity coupled to matter fields. Okay, and this includes in particular string theory. So in this we will consider an S matrix element that involves arbitrary number of external particles of finite energy and one external graviton carrying small momentum, okay, which I denote by K. And soft graviton theorem is a relation between the K goes to 0 limit of this amplitude and the amplitude without a graviton. So that's the content of the soft graviton theorem. So the order K inverse term, these you will see is the leading contribution. So the relation involving the order K inverse term is what is called the leading soft graviton theorem. And then the constant piece is the subleading soft graviton theorem. Okay, and then you can go one more order, but I will not discuss that today. Okay, this is something that I am doing with all of. Hopefully there will be a subleading soft graviton theorem. So what we will show is that the leading and the subleading soft graviton theorems are universal. In particular, the form of these theorems do not depend on the theory and it holds in full quantum theory. Okay, irrespective of what theory we are considering. Limitations are that we have to work in non-compact space-time dimensions d larger than or equal to 5. Okay, that time we of course compact space-time dimensions also, compact space dimensions. And this is necessary in order to avoid infrared divergences. Okay, because you know that gravity in 4 dimensions is infrared divergent. Okay, the S matrix element in fact is not well defined. So if we want to discuss soft graviton theorem in d equal to 4, we have to restrict to 3 amplitudes. Okay, for 3 amplitudes, of course, there is no infrared divergence, and this analysis will hold for d equal to 4. So this is what you have to keep in mind. Okay, and this is a generic feature of all quantum theories of gravity in 4 dimensions, that the S matrix elements are infrared divergent. So you cannot really write down sensible relations involving S matrix elements themselves. Okay. So the idea is that we have to will divide the set of Feynman diagrams into 2 parts. Okay, so this analysis will be perturbative. So I am using the language of Feynman diagrams. But as you will see, you don't have to restrict to any given order in perturbation theory. So you have to consider 2 types of Feynman diagrams. In one type, the soft graviton, which is denoted by this thin line over here, attaches to an external line via 3-point vortex. And here I'll use the language of 1pi vortex and amputated Green's function. So amputated Green's function is a Green's function whose external legs have been removed. So this gamma here will denote amputated Green's function. For 3-point function, this is the same as the 1 particle irreducible vortex. The internal lines, in particular this one, will represent fully normalized propagators. Epsilon and k will be the polarization and momentum of the soft graviton, as you can see here, and the epsilon I and pi, which are these are the polarization and momentum of finite energy external particles. So this is one class of diagrams you have to consider.
So sorry, I missed about amputated Green's functions. You're just saying it's a standard notion, you remove the external.
You remove the external legs. So this, for example, the way you should interpret this, that all the external legs are removed. Okay. Even this is removed in the definition of gamma. Okay. But in this thick internal propagator, you have the full internal propagator. Okay. So this is the full Feynman diagram of this structure. Is this okay? So the same diagram again. And now the point I want to emphasize here is that this is a full Green's function, right? So there is in general mixing between different states. Okay. But let's consider a particular propagating state here, which has the same mass as the external state, okay, which I will call AY. In this case, the internal propagator will give bi plus k whole square plus mi square inverse. There are of course various numerator factors which I have not written down. And now, using the fact that the external legs are on shell, so we have pi square plus mi square is 0, and of course k square is 0. That's the graviton momentum. we see that pi plus k whole square plus mi square is just 2 pi dot k inverse, and this is the origin of the pole. Okay, so this diagram goes as k inverse. So this then contributes at the leading order, and once it contributes at the leading order, in general it will also contribute at the subleading order. Okay, and further on.
And is it the only contribution at subleading order as well?
No, this is not the only contribution at the subleading order. So leading order, this is the only contribution. Okay, with this line attaching to various external legs. But at subleading order, the other diagram will come.
I mean, when you say this is the only contribution, you mean any number of EI, PI, that is, I didn't fully understand that.
Yeah, the soft graviton has to attach to one of the external lines.
Only one.
Only one. Because if you attach two of, suppose you take P1 plus P2, right? Then P1 plus P2 whole square is far off shell, right?
Okay.
So in general, there is no, I mean, you are assuming that you are not sitting on the poles for the PIs, right? So generic external momentum, right? P1 plus P2 is off shell momentum. So there will be no poles. Is this okay? Oh, this is the second class of diagrams. Okay, this is basically everything that is not included in the first class, where the soft graviton gets attached to this block gamma tilde. Okay, so this denotes amplitude and amplitudes as before, all the external propagators are cut off. And there is further restriction that the external soft graviton does not get attached to an external line. Okay, which basically means that gamma tilde is everything except graphs of this line. So this graph has no pole as k goes to 0. So this means that at the leading order this doesn't contribute, but at the first subleading order it will contribute. Okay, because the leading order is k inverse and the first subleading order is order 1. So you have to analyze both of these class of diagrams if you want to get the result up to first subleading order. Questions? So now I'll outline the strategy for doing this calculation. And you can see at some level this diagram is easier to handle, because if we are trying to relate this amplitude to the one without the soft graviton, okay, we already have a piece here which is like an amplitude without the soft graviton. Okay, so you might expect that this is easier to handle, but of course here you have to go to one subleading order, right? So it's not, so that makes it a little more difficult. This diagram on the other hand a priori has no relation, right? The soft graviton just gets attached inside. So there is no obvious way that you can remove this soft graviton. Okay, but we will see that there is a way to do this as we go along. Okay. So strategy for doing this calculation, we will be working with one particle irreducible effective action of the theory. Okay, which means that let's assume that you have already done all the loop integrals and you have gotten a one particle irreducible effective action, which is still gauge invariant. Okay, so you basically do the loop integrals and then you subtract off the gauge fixing term, right? That's the way you get gauge invariant one particle irreducible effective action. Okay. The advantage is that with one particle irreducible effective action, you only have to do pre-level calculations. Why we want to do this will be clear later, but it's actually not very strictly necessary. We could work with even with the full finite apertures. So the information that we will be using is that it should be invariant and a general coordinate transformation or other gauge techniques. Okay, because one pi effective action is still gauge invariant, because we do the calculation and then remove subtract all the gauge fixing term. So now we will assume that this action has an extremum at g mu nu equal to eta mu nu at the matrix. So this is Lorentz invariant extremum. All the other tensor fields are set to 0, and the scalar fields take some suitable vacuum expression values depending on the effective potential that you get. So this is a general situation, but the assumption is that there is a Minkowski vacuum. Now we take this action and we expand it in powers of fields, including the metric fluctuations, around the extremum of the action. Okay, so you do it for all fields, including the g mu nu, you now write as eta mu nu plus kappa h mu nu and expand it out. So in this expanded action, we now add manifestly Lorentz invariant gauge fixing terms. Okay, because we have to do two-level calculation, right? So we need the propagator, so we have to add a gauge fixing term. So So basically we add back the gauge fixing term that was there to that was used in the computation in the first place. So after we do this, the resulting action will be manifestly Lorentz invariant, but not manifestly general coordinate invariant, right? Because the gauge fixing term typically will break general coordinate invariance because you are fixing the gauge. Is this clear? Now comes the main point. So we will use this action to compute amplitudes involving finite energy external states, but not amplitudes in soft external gravitons. Okay, for these we will be using a different procedure. Okay, so this action, so if you are trying to compute the action load to soft graviton, amplitude load to soft graviton, this is the way we will do this calculation. Okay. Now we come to soft gravitons. Okay, how do we deal with soft gravitons? So here you have to use a different approach. Well, you don't have to, but it's easier to use a different approach. And the reason that this is okay is because with 1 pi effective action you only calculate 3 terms, right? So there is a clear distinction between which lines are soft and which lines carry finite energy. Okay, in fact, in general only the external line will carry soft momentum. All the internal lines carry finite energy. Okay, because it's getting attached to one finite energy external line. So all internal lines carry finite energy, and only the external line is soft. So it is possible to treat the soft graviton as a particle that is different from the finite energy graviton and other particles. Okay, we just think of the soft graviton as a new kind of particle and we treat it differently. Okay, because it's new just because of momentum. Okay, the momentum it carries is soft. Yeah, and there is no mixing because no external line carries soft momentum, so there is a clear distinction between what is soft and what is finite energy. Is this okay? This is going to be an important point.
I mean, you can distinguish because you are thinking of some power series expansion in 1 over k. I mean, in the sense that really speaking, it's a continuum.
It's a continuum, but the point is if you use 1 pi vortices, right? When you draw the Feynman diagram, right? There is one external line which is soft.
Right.
Everything else has finite energy. So you just put some arbitrary cutoff.
Okay, you put
Call the momentum below that cutoff as soft, the momentum above that cutoff has finite energy. And you don't have to worry about there being any overlap because all internal lines carry finite energy, only one external line carries soft, right? So there is a clear distinction between the soft and the finite momentum. So this continuum that you are talking about, you will never see anything in the continuum, right?
for a particular diagram.
For a particular diagram, exactly. Good. For a particular diagram, for a given set of external states,
Yeah, okay,
right? I mean, you never see any continuum, right?
Yeah.
So this is the place where
begins at some particular
Exactly.
energy.
exactly. Okay, so this is where the using 1 pi effective action is useful, right? Because in terms of 1 pi effective action, you can see that there is never going to be any overlap between the soft and the finite energy particles.
Sorry, I'm missing something. So if you didn't have soft gravitons, you took the 1 pi, and then you have to compute 3 graphs from there, so you fix some gauge, and you do it. And you don't do, I mean, a soft graviton is after all another particle just with a small momentum.
Yes, you could have done it that way.
You could have done it
You could have done it that way. That would make things more complicated.
I see, okay.
I'll do it in a slightly different way.
And just to understand, the different ways, again, you have an external leg which is soft, but the way you're incorporating it
In
is
the action
in the action.
is different.
And
Yeah, I'll describe how it is.
okay.
So this is just a prelude. Okay? So now I'm going to tell exactly how I deal with the soft graviton.
Okay.
Okay?
But at the moment you're saying it's easy to tell which external legs are soft.
Exactly. And even internal, right? All internal legs are hard.
Are hard, okay.
So it's easy to tell the soft from the finite energy ones, right? That's the only thing what I'm doing. Okay. So now how to incorporate the soft graviton. Okay, so to calculate the coupling of the soft graviton to the rest of the fields, we basically take this gauge fixed action and covariantize it. So when I mean by covariantize it, is we replace the background metric eta mu by eta mu plus 2s mu and replace all derivatives by covariant derivatives computed to the metric eta mu plus 2s mu. Now this is automatic if we have a gauge invariant right? There, of course, if you want to look at the coupling of the soft graviton, you just covariant guys. Okay. But what this is saying is that even the gauge fixing term that you have added, they are also covariant as with respect to the soft graviton. Right. Question. Yes.
Ashok, I had a question.
Yes.
So regarding this effective action,
Yes.
this effective action that you treat soft graviton differently, it is same as the Wilsonian action at the infrared cutoff.
Well, see here, I mean, you could perhaps think of it that way, but I am first of all assuming that I am in higher than 4 dimensions. So there is no infrared cutoff that is necessary. I make a sharp cutoff between what is infrared, what is ultraviolet, because I am only doing 3 amplitudes, using 1 pi graphs. And I just treat the particles that are below that cutoff differently, right? That's all.
Okay. But even if you are in high enough dimensions, it's still true that the 1 pi effective action, the total 1 pi effective action is non-local.
It's non-local if you try to expand in very high order.
Yeah. Okay.
If you try to make a derivative expansion, right?
Yes.
So I'm not assuming here that you have tried to make a derivative expansion. Right? It's given by some function of the momentum.
So, but this treating soft graviton differently, does it cure the non-locality or?
No, it doesn't cure the non-locality, right? It will be treated as some function. So the way we will write the 1 pi effective action, that suppose you work in the momentum space, right? It will be a product of fields in the momentum space multiplied by some function of the momentum. Okay? That's the general structure of the 1 pi effective action, right? And that function, there is no problem in defining that function for any PIs. Okay? If you try to go on shell, see, even in 4 dimensions, this 1 pi effective action can be defined without any problem, right? Off shell 1 pi effective action. In 4 dimensions, what will happen is that if you try to take some of the external lines on shell, then you start seeing that the action diverges. Okay, that's the infrared divergence. If you are in higher dimension, then you can take the on shell limit to calculate the S matrix without encountering the infrared divergence. But at this level, you can think of this as an off shell 1 pi effective action that we have, that we are covariantizing. Right?
So I just have one more question.
Yes.
Different question. Which is that do you treat all the other light particles? Let's say if I had a photon also in the problem.
Yes.
Would you also treat that as a neutral particle?
Yes, that even the graviton. See, I am assuming that you don't have any soft photon, right? All external particles are finite energy except the graviton. So even the finite energy external gravitons I treat as a different particle.
Okay.
Because basically that point is because at tree level there is a clear distinction between which line carries hard momentum, which line carries soft momentum. Right? I am using the 1 pi vortices. So there is no problem in identifying what is soft and what is hard.
So the question was treating all the soft particles as different particles?
There is only one soft particle. I am considering a soft graviton amplitude with one external soft graviton. If there are multiple soft gravitons, yes, then all of those will be in one kind of particles. The others will be, the finite energy particles will be different particles. But in this problem, I am only going to consider one soft external graviton. So in the Feynman diagram, there is only one particle which is soft, which is treated distinctly from the others.
Yeah, thanks.
Is this okay?
Yeah, okay.
What about internal legs? Can you have soft particles in the internal legs?
See, by momentum conservation, you cannot have soft particle in the internal leg.
2 of them?
2 of them? No, because see, again, this is, I am drawing only 3 graphs, right?
Oh.
Because I am using 1 pi graphs, right? So in the, otherwise of course in the internal leg there are soft particles and those are the ones which cause problem in 4 dimensions, right? Give rise to the infrared divergences. Right? In higher dimension you don't have that problem. Is this okay? Okay. So the point is that the gauge fixing term that we have used for the H mu, for example, right? Which is the hard part of the matrix. Okay. I am covariantizing with respect to the soft part. Okay. So instead of writing del mu H mu square, right, which is the standard kind of gauge fixing term on X, I will write d mu H mu square, where d mu is covariantized with respect to the soft. Right. And this makes the whole action covariantized with respect to the soft.
Why do you have the factor of 2?
Oh, that's just because I want to have 1 in the fear lines. So 2 in the metric is used to this. Right? And in fact, normally one expands h mu, it's 2 kappa h mu, right? That's just some knowledge.
Sorry, why did you do this?
Why do I do this? Because this allows you to determine the soft graviton coupling simply. Right? We'll see what is the advantage of doing this. Right? I could have done the calculation by treating the soft graviton as in the same way that I am treating the finite energy lines. Right? Is that they are extracting the amplitude is more complicated. Will be more complicated. Right? We will see the advantage of this.
Doing this, this is something, is there a reason for doing this? You are inventing a method of getting the same amount of computation.
It's the same amplitude. Because S matrix, which is gauge invariant, right? It doesn't depend on how you choose the gauge fixing term, right? All I am saying is that I am choosing the gauge fixing terms in such a way that they are covariant as with respect to soft graviton. Okay? The final S matrix should be independent of how you have chosen the gauge fixing term, right? If instead of using d mu h mu nu square, right, I had used del mu h mu nu square, the final result should be the same, right? But individual diagrams will have different contribution. Okay? This will make it easier to extract the contribution from the individual diagrams that we described, right? Gamma tilde and gamma. Then we will see that both become simple calculations.
And besides the gauge fixing terms, even the part of the action which was general coordinate invariant, you expanded it about determinant,
Yes.
right? And then there also the derivatives which appear,
Are ordinary derivatives.
Ordinary
Now I am
derivatives.
covariantizing them with respect to soft graviton. Exactly.
and that's for that part of the action, it's a little bit like splitting the full metric into some sort
That's
of
right.
cluster.
Exactly. Exactly.
So you have two different ways of tagging the gauge invariance. One is to use background gauge invariance
Yes.
for S mu nu
Yes.
and standard BRST or
Exactly.
whatever for H mu.
Exactly. So you can think of the soft graviton being treated in the background
Background gauge.
by using the background field method. Normally in the background field method you use the whole
Yeah.
field, but here the soft graviton I am treating in the background field method.
Right.
Others are just standard.
Like yeah.
Exactly. Okay. Now this, of course, visas subterms. Okay, if you try to get this coupling, these will miss terms which involve Riemann tensor computed from the metric. Okay? Because if you have when you try to covariantize a given action, right, you can have coupling of the Riemann tensor computed from this eta mu nu plus 2s mu nu metric, right, and couple it to the rest of the finite energy fields. Okay? Those terms will not be captured by this covariantization procedure. But those terms have two derivatives of the soft graviton. Right? Riemann tensor involves two derivatives, that means two factors of the soft momentum. So if you are interested up to subleading order, these terms are not going to contribute. At the subleading order, you have to worry about these terms. Right? And that's the reason why the subleading soft graviton theorem is not universal. Okay? It can still be controlled, but it's not universal. But if we ignore these terms, if we are only interested in corrections up to the first order, first subleading order, then you don't have to worry about this. Okay, so we don't miss anything. Okay, so by this procedure, the action that we get will be invariant on the general coordinate transforms of the soft graviton field, right? Because that's the way you have covariantized it. But we don't need to gauge fix, okay? Because soft gravitons will only appear in the external leg, right? We are never going to worry about the calculating propagators of the soft graviton. Okay, so there no gauge fixing is necessary. We can just work with this action. Is this clear?
Why does it, didn't fully understand why it misses these terms. I guess they're not important, but I mean, if I took just the general coordinate invariant terms and I split the full metric as soft plus something, and can't I get a contribution from S mu nu towards the Riemann?
You can get, but sometimes you may miss some terms. Okay? See, for example, if you use this kind of gauge conditions d mu h mu nu, d mu h mu d rho h mu, term like this, right? So the procedure I am suggesting is that you first do the put the gauge condition del rho h mu rho, del mu h mu, right? Then you covariantize it. But that is somewhat ambiguous because suppose you write this as h mu rho del rho del mu del rho del mu h mu, right? At this level they commute. Right? So whether you replace these by covariant derivatives after commuting or before commuting will make a difference. Right? So these terms are harder to keep track of, right? In principle, if you are very careful from the beginning, you can keep track of them, but you have to worry about these.
So from the gauge fixing terms, I guess the ambiguity.
Exactly. From the gauge fixing, from the ambiguity may come. Right? Even from the metric part. Suppose you have a high number of derivatives in the action. Okay. Then how you first linearize it, you expand it out, right? All covariant derivatives are replaced by del mu. Now you are replacing the del mu by d mu, right? And which order they were to begin with, that information has been lost, right? When you have expanded it out. So you may get corrections, right? It's clear that if you are careful, you can keep track of them, but it's hard. You cannot just get a simple prescription.
Yeah, just the process of covariantizing is not.
Yeah, the process of covariantizing is not well defined, right? Because you have destroyed the symmetry between the soft and the hard parts by this process. Okay. Now, some more strategy for this is for simplification. So you'll be working to first order in the soft graviton field because you are interested in one soft graviton. So we take the soft graviton field to be epsilon mu into the I k dot x. This is the polarization, this is the momentum of the soft graviton. Epsilon I take to be symmetric, traceless, and the k mu epsilon mu equal to 0. So that's the gauge condition that we'll be using. So because we will be working in first order in the soft graviton field, whenever I raise or lower index, it will be by eta. Okay? Anytime I use actual graviton field to raise and lower index, I explicitly put in the factors of s. This is another simplification. Okay, again, none of this is necessary, but this makes life simple. So we take all fields that represent finite energy external states, we take them to carry tangent space indices instead of the curve space indices. So h mu nu, suppose you expand the Einstein action against h mu nu, right? I treat the h mu nu as a tensor field, okay, carrying HAB, that tangent space indices. Of course, when you have expanded out, it makes no difference, right? But it makes a difference when you covariantize, right? When you covariantize, whether you think of these as tangent space indices or curve space indices, determines whether you are using spin connection or the disturbance symbol. Okay. So I will take them to be flat space indices. So I will be using spin connection to covariantize. So this has the advantage that this allows us to give uniform treatment to formulas and bosons, because for formulas you have to use spin connection anyway. Okay, so you just make everything, all fields in the tensor, in the carrying flat space index. S matrix of course doesn't depend on that, right? It's just field definition. Okay, and finally the wire bands that I'll be using to contract tangent space and curve space indices. Okay, these are square root of the metric, but I'll take what is called the symmetric square root. So E mu A, these are the usual wire bands, is delta mu A plus S mu A, that's the square root of that is square root of eta mu plus 2S mu. And these are the inverses, okay, which is just with the minus sign to this order. And again the indices are raised and lowered by eta mu. And the inverse metric is given here. Is this okay? Okay. So now we begin our analysis, but before doing that, this is just introducing a set of notations. So this is the amplitude without soft graviton. Okay, we want to express everything in terms of these amplitudes. So this I'll use this label that, so there are these polarization tensors. Okay, I'll use a polarization tensor epsilon 1 alpha 1 to epsilon and alpha and pn. And then this is the tensor with which is contracted. Okay, each alpha I are some tangent space tensor or spinor index. In fact, I'll use a notation in which information will be in the epsilon. So epsilon will have support only in a certain set of fields, but the alpha index are let run over all fields. Is this?
I did.
Yeah. So I take, suppose phi alpha is the set of all the fields. Okay. Every polarization tensor, okay, the number of components of polarization tensor will be the number of fields for it. Okay. Suppose you have graviton, scalars, vectors, right? Every alpha, right? Every index alpha will run over all the.
So the polarizations plus species number, species label is your full polarization. Right?
Exactly. That's right. So alpha basically includes not just the Lorentz index. Okay, that's why I said it's in general a reducible representation. Okay, alpha is just running over the whole thing.
All external states.
All external, all fields, right? Not just external states. So alpha will run over, in string theory of course there are many auxiliary fields, right? So alpha will run over everything. Okay, all the fields that are there in the problem. Of course external states, epsilons, have to satisfy all shell condition. Right? So those will be restricted. So epsilon will have only certain components non-zero, everything else zero. Right? A given epsilon.
So it's a huge column vector with spinors, bispinors, trispinors, blah blah
Everything.
blah, the
Exactly.
whole lot.
Everything.
And the epsilon, some of the epsilons will live among the spinors and some.
Exactly. That's right. Okay, that's the notation because that will make life simple because I can just deal with the whole thing at one go. Is this clear? Okay. So now this is a shorthand notation, gamma alpha I. So this basically is the notation for the contraction of this gamma with all the epsilons other than the ith one. Okay, I have just introduced this symbol because it will be easier to express the final things in terms of these. So gamma alpha, so it carries alpha index explicitly because epsilon is not contracted. All the other indices are contracted. So this in fact has a hidden dependence on all the other epsilons, right, and all the other momenta which are not just labeled here. This is clear? This is just a notation that we strip off. So gamma alpha pi is just this amplitude where you just strip off the epsilon I factor, okay, and contract everything else.
Sorry, since you're taking this abstract view that gamma has values for all alphas and so on, only those, if you're populating an epsilon, it is non-zero, else it's zero. According
Yeah.
to some
So gamma alpha I, see this will alpha index will run over all possible
Yeah. This one is
fields. When you contract with epsilon, right, it will only pick up certain components. Right, that's the notation. So each of the external labels will be over all fields.
And this includes both soft and hard.
No, soft fields will be soft field. There is only one soft field that has been always getting separate. Okay, they are all hard fields. Okay. So now we start with this diagram. So this diagram, as I said, is difficult in some sense because it doesn't have manifest factorization property that epsilon is just sticking into the diagram. But here you only need the leading contribution, right? That's the simplification. So let's see how we can get the leading contribution. So since we need only the leading contribution, we can just set k equal to 0 and try to calculate this. Okay, because we are looking at the expansion in powers of k.
because there's no 1 over k piece.
Yeah, because this has no 1 over k. Okay, for the other one, we have to first extract of the 1 over k pole and then we can try to do an expansion in powers of k. So now, if we set k equal to 0, how can we extract the amplitude? So we can take the diagram without the soft graviton and change the background metric to eta mu plus 2x epsilon. Okay, suppose you do that. And then you expand in powers of eta mu, epsilon mu, you just keep the term linear in epsilon.
Epsilon mu is constant or a function?
Epsilon mu is a constant because you have set k equal to 0. Right? Because k equal to 0, epsilon mu is just a constant. Right? Okay. So just shift the eta mu by a constant shift epsilon mu.
So when you put k equal to 0, the transversality condition basically means unit vector. I mean k hat mu epsilon mu nu equal to 0 because the right.
This one.
If you go
Well,
by
see, okay, for this,
transversality condition,
I
it
agree.
makes sense only if you replace the k mu by the unit vector.
yeah, I agree. So for this problem, for this, see, we don't even need that. We will not need the KMU epsilon mu equal to 0, right? That will be needed for the other diagram when you actually have to do a power series expansion. Okay, so for this, we can forget about it. We can assume that epsilon is restricted. We will need the epsilon mu equal to 0 condition, tracelessness condition. But the epsilon mu k we don't need. Okay? Because we are just evaluating this by setting k equal to 0. So this is what we need to do. Now we can do it in two different ways. One is that for every internal vortex and propagators that it has, we make this replacement. Okay? That will generate a coupling of the soft graviton to that vortex or coupling of the soft graviton to that line. Okay? That's the picture. But we can also do this in the final amplitude. Right? Imagine that we first calculate the amplitude in flat background, right, without the soft graviton. Take that amplitude and in that amplitude replace wherever eta mu has appeared or wherever you covariantize, right? You are supposed to replace eta mu by eta mu plus 2 epsilon mu, right? The metric has been changed. We make this replacement in the final amplitude. Okay, that's equivalent to making this replacement at whenever the metric is supposed to appear in the internal line, right? You replace it by eta mu plus 2 epsilon mu. Right? Or whether the PR line is supposed to appear, you replace by delta mu plus S. So let's see what this means, then maybe it will become clear, right? So suppose we are trying to do this in the final expression for the amplitude, okay? So now we can see that if you take the final expression for the amplitude, what structure does it have, right? It's function of some p mu's and some alphas, right, which have been contracted. Now because alphas have been taken in the tangent space level, they are always contracted by eta, even in the presence of non-trivial background. So for alphas you don't have to do anything, they are contracted with etas. Whenever there is a derivative or momentum factor, they are in the Chord space index. So you have to convert them using the Fiat line, right, to the tangent space index. Once you have converted to tangent space index, then you convert everything by contract everything by etas. So the only change that you have to make in making this replacement of g mu nu by eta mu nu plus 2 epsilon mu nu is that we make sure that the momentum indices are now contracted by this. Okay, the momentum indices, the space-time level that the momentum factors can carry, they are first converted to tangent space index by this inverse Fiat line, and then we can use eta. So now the epsilon dependence. Is this clear? So this means that we basically replace pi mu. Okay? We are basically contracting this with pi mu, right? We replace pi mu by pi mu minus epsilon mu nu pi mu, and then in the final expression we pick the term linear in epsilon.
This is sort of like equivalent to doing the coordinate. There will be a constant coordinate transformation that
Which will undo this, exactly.
Yes.
There will be a constant coordinate transformation which will undo this change in the metric. It's a constant change in the background metric, right? So you undo this by constant coordinate transformation and then you pick up the.
But then the alphas will also be contracted.
No, that's why I took the alphas in the tangent space level, right? The tangent space indices are always contracted by eta, even when its coordinates are changed, right? If you have taken them in the Chord space index, right, then you have to convert them by metric, right? Then they are more complicated terms, right? There's an additional term which will have a similar replacement for each of the tangents of those polarization indices, right? But because I have taken the polarization indices in the tangent space level, right, we don't have to rotate them. Okay, you can verify that if you do it the other way, it gives some extra term, but at the end those terms cancel. Okay, but this is similar because you don't have them in the middle.
You say the difference is just a labeling for your epsilons.
Just label, or it's a field redefinition. See, this diagram by itself will not be invariant under that change. Okay, because in each epsilon will have to be changed, right? But then you have to now, instead of using the, when you do the other diagram, okay, instead of using spin connection, I have to now use Christoffel symbol to covariant, right? And that will basically compensate this one. Because changing from the, what is the difference? Suppose you have a Maxwell field, right? You can think of this as AA, which is carrying tangent space level, or A mu, right? What is the difference? A is EMU, AMU, right? That's a field definition. And the S matrix doesn't change by field definition, right? So that's what it is doing. But individual Feynman diagrams will change that field definition.
Ashok, can I just ask a dumb question? I mean, is this, suppose for a moment there was this theory of scalars and gravitons, and I'm just interested in some scalar endpoint function with one soft graviton insertion. Then I could naively, just to understand what you're saying, I could naively do the following, that I introduce the coupling to the metric as a perturbation through the stress energy tensor of the scalar, and then if I am interested in some soft graviton limit, then that will give me some integral of the stress energy tensor, which will be either energy or some Lorentz generator or something. Is this procedure roughly?
Yeah, I think it's roughly that. But except that you cannot really restrict to scalars, right? Because
you have
a scalar scattering, right?
Yeah.
Suppose you have a hard scattering of the scalars, right? There are gravitons being exchanged here, right? And when you talk about inserting soft graviton, right? The soft graviton can come and insert here, but it can also insert here. Okay? So you have to deal with the whole thing at one go, right? So you can either replace in each coupling. We have to replace this eta mu nu by or the metric. Whenever the metric is supposed to appear, you will replace it by eta mu nu minus 2s mu nu. Or you first do the calculation and then covariance it. Okay.
I can see how this trick works for a single soft graviton thing, but I
yeah,
say
for multiple, I am not going to deal with multiple ones. Okay. For multiple ones, it will be more complicated. It should still work because the philosophy is the same, right? That to the leading order, right, the coupling is determined by covariant. Okay. It's only when two derivatives come in, right, that covariant is not enough. You have to do more work.
When you're labeling your internal states, let's say you're labeling the polarizations of the internals, of the external states. Now this label depends on the momentum that's going into the into this state.
The epsilon depends on the momentum.
The epsilon depends on the momentum. Yes. I just want to understand how there's some convention now when you change your metric to metric plus your small correction. You could also have changed your state a little bit.
Yeah. So I'm not doing that. This is offset. I'm not at this for this part of the calculation. Yeah. I'm not assuming there is any relation between epsilon and B.
I see.
Okay. Nothing that I have said requires this to be on shell.
I see.
I take the epsilons to be independent of B.
I see.
Okay. Eventually, I have to use the on shell condition on epsilon, okay, but not for this diagram.
Okay.
Sorry, I'm going back a bit, but so your leading order is 1 by k and first subleading is 0, right?
That's
so,
it, yes.
How do you know there is no intermediate piece, say of something like log k?
Well, in 4 dimensions there are, right? But once you go to sufficient, see this log case comes from the internal loops, right?
Okay.
Not 3 level will not give log k.
Okay.
Right? So once you go beyond 5 dimensions, right, then you can check that there are no corrections. Okay, so is this clear that we just change the piece by this? Okay, so the final amplitude is just given by this. Okay, the linear piece in epsilon is just epsilon mu nu pi nu del del pi nu. Okay, each pi has to be changed by this amount. So this is a shorthand notation of this. Okay, at this level, in fact, I didn't have to do this. I could have put all the epsilons inside, but I have used this notation because eventually, as Siddharth said, this epsilon I will start depending on pi. Once you start put the on shell condition, right, then these will start depending on pi. So I absorb all the other epsilons inside gamma because that can go through the derivatives, and I keep this outside. Okay. Now, just to emphasize that this is really optional, that this is not gauge invariant. Okay. In fact, you can see that suppose you take this gamma I here, okay. You can add to that a term proportional to pi square plus mi square, okay, which vanishes also. Okay. It will not change the S matrix, but it will change this, right? Because if you add something proportional to pi square plus mi square, the LL pi mu will give a term proportional to pi mu, right? So it's epsilon mu nu pi mu pi mu, right? So this term is non-zero. So this is not gauge invariant. This requires an optional continuation. We'll see the final result doesn't require optional continuation, but this one does. Okay, once you combine it with the other term, okay, this will go away. Yeah, I'm saying that if you look at this formula, suppose you add to this gamma alpha I a term proportional to pi square plus mi square. Right? That term vanishes on shell. Right? So it doesn't affect the S matrix of the S matrix without the soft graviton. Right? But if you add such a term here in the expression for gamma I alpha I pi, you will get a term proportional to pi by differentiating, right? And you get epsilon mu nu pi mu, which is non-zero in general. So this result is sensitive to what is your optional continuation, right? Different gauge fixing choices will give different results for this, right? Because they will give different optional continuation. Is this okay? So this is basically all you have to do for this diagram. Okay, this is the result for that diagram. Now we turn to the other one. So now if you look at this part already has the structure of an amplitude without the soft graviton. Right? Because all that has changed here because this line has carried momentum pi plus k, but there is no soft graviton inserted here. So basically you have to focus on this one. Okay? This is what the soft graviton is being inserted. But now we have to be a little more careful because we have to what? To first subleading order. So covariantization does not only mean we have to change the metric eta mu nu to eta mu nu plus epsilon mu nu or 2 epsilon mu nu. We also have to introduce the covariant derivatives.
But sorry, if the leading order soft graviton theorem you told us what it was, that is what is the 1 over k piece?
No, that will come out from this. Yeah. So leading order part of this is again very easy to evaluate. I will do the same thing that I did for the earlier one, but for this amplitude. See, if I want the leading part of this, right, that can be done by the previous procedure. So the subleading one is a more complicated one, right? So I'll do both at one go. This is subleading because this doesn't have a 1 over k, right? Okay. So basically we focus on this, extracting this 3-point function. And the strategy again is that we first look at the 2-point function without the soft graviton and then covariantize it. Okay? So this is the most general form of the 2-point function. Okay? Phi alpha is the set of all the fields in the problem. K alpha beta is some kinetic term. And I can choose without loss of generality this symmetry condition that K alpha beta of Q is equal to K beta alpha of minus. Okay, that's just this exchange under alpha beta and Q1 Q. Okay, I'll assume that K has been taken to be so. Now let's look at the effect of covariantization. Okay, in the way that I have written here, all the derivatives act on the second phi beta. Okay, that of course you can change by integration by parts, but this is just one convention for all derivatives because it's a function of Q2 only, it all acts on phi beta. So acting on phi alpha, well actually I should have made it phi beta, maybe doesn't matter. So what is the replacement rule? So del A, okay, this is an ordinary derivative. I have just used the index A, okay, but it's not tangent space, it's just space time. But when you covariantize it, I have to write it as EMU dmu. Okay. So this EMU I write as delta mu minus SMU, and dmu I keep as it is here. Okay. So dmu I have given in the next slide, next line. So dmu phi alpha is given by this. This is a spin connection, okay, which written in after the soft plates is given by this. And GAB, this is angular momentum generator. Okay, this is angular momentum generator in this big space. Okay, but of course it acts block diagonally, okay, in different sectors.
So once again, this replacement is done after all the derivatives, after all the partial integral has been done, and all the derivatives are placed on phi beta.
That's it. I'm assuming that that's how I have structured the action, but it's not necessary. Okay, you could have distributed, it just makes life a little simpler to have everything on one file.
But again, multiple derivatives would have caused the same problem.
Yeah,
as we said
so
for
this,
Riemann.
so this problem, the Riemann, I'm ignoring for this. Up to subleading, we have seen the Riemann is not necessary, right? Because that includes two parts. But if you want to keep track of the Riemann, yes, then you have to worry about that as well.
And there you can say now there's a prescription that I do all the partial integrals, I put all the derivatives on phi, and then do this replacement. That's a unique prescription.
Yeah. Okay. So now let me say one thing. So first the normalization of J. Okay, normally there are factors of I, etc. hanging around here, but I have normalized J such that I'm acting on a covariant vector field. JB is just this. Okay, so this fixes the normalization, and with that normalization, what I have given in the previous slide is the correct form. Second point is the following. See, I replaced, it is true that d mu on phi alpha is this. But I am not assuming that k alpha beta is only linear. Right? K alpha beta is in general has a lot of derivatives. Right? It's a non-local, in general it will be a function of derivatives. Imagine that it has two factors of d mu phi alpha, right? So then, in this case, you will also have to introduce a Christoffel symbol, right? Because the second d mu acting on the first d mu will have a gamma rho. So I'll ignore this for now. I claim that all such terms cancel if we have with the convention that we have taken for a claim. Okay, I'll try to argue it separately. Right now we are just ignoring. We'll ignore this and proceed.
Sorry, so ignore that.
Ignore this gamma terms. Right? So in the previous one, right, I said that d mu phi alpha is this. When I put say d mu phi alpha, right, I'll still use this form of the replacement, right? Ignoring the gamma terms. That is what. Okay, and the claim is that they cancel. Okay, they don't contribute. Is this okay? Okay. So now let me say what the covariant interest is. So this was the original action, right? So when you try to covariantize, so you have this factor delta d q1 plus q2 k alpha beta q2. This gets replaced by the same delta function. You see that q1 plus q2, you may have wondered for that inside the delta function, when you replace q by the epsilon mu nu q nu, right? Whether that can change, but that to leading order you can clearly see that that doesn't change anything, right? Because of the case of epsilon being 0, right? The delta function is the same. Okay, and you can check that this also doesn't change anything in the subleading order.
Yes, so you're saying that delta has a 1 over square root of g in it.
Exactly.
And then determinant of g is 1 plus trace g, and that's
That's what. Yeah. Okay. So replacement rule is that this will be replaced by this minus. First of all, because of this e to the I k dot x. See, e to the I k dot x, epsilon mu, that soft graviton is epsilon mu into the I k dot x, right? So terms linear in epsilon mu is always carried into the I k dot x. So that makes the delta momentum conserving delta function change from delta q1 plus q2 to delta q1 plus q2 plus k. Right? Because you have phi x, phi y, phi alpha x, phi beta y into the I k dot x. Okay, that change is always here. This is the change because of the change in the. This is the change that we discussed previously. Okay, that every momentum factor will come with this e mu a, which will give this change. And this is the change that is induced because of the spin connection. You can see why this is the case. So what does it mean? Okay. you see the derivative with respect to q tu, right? So where is it coming from? It's coming from the fact that this replacement has to be done for every derivative. Every del mu is replaced by this, right? So in general, if you think of k alpha beta as a function of momentum, for every momentum factor you make this replacement. So this means that you take the derivative of k with respect to momentum and multiply by the shift in the momentum, that is this one. Is this clear? That's the second term. Okay, this is the omega mu nu written in the momentum space, and I do it for every factor of q2, that is Is this okay?
So I didn't understand why that omega is equal to k. Sorry, I just
Oh, this omega?
Yeah.
Oh, because this has derivative of the soft graviton, right? So this brings an ik
Yes,
basically, right? So iq is replaced by ik.
I got confused. I mean, you have this expression.
Yes.
Alphas are tangent space indices, right?
Alpha and tangent space indices, yes.
Then why is it not enough just to keep that first term where you
This one?
No, in the next transparency.
Oh, why gamma? Why gamma?
I think the next one.
Sorry, I meant not the one before, but after. Yeah, exactly. So the first term here itself.
It is converting the tangent space index to the curve space index to tangent space index, right? So let me see. Suppose you have d mu phi alpha, okay, then d mu phi mu, right? Okay. So how will you write this? So how do you covariantize it? So maybe I write del mu.
I mean, what I was asking, I didn't understand why you had a second term in that. When we went through the similar thing for the second diagram, you didn't have any such terms.
Yeah, because this has to do with for subleading order. So you are doing, we have to, this term is subleading, right? Because it has a derivative with respect to, which has a k factor, right?
The spin connection part was
Yeah, the spin correction part I could ignore in the second diagram, right? If I want to go to subleading, then I have to keep the spin correction part in the second diagram also. Okay, so here that what is happening? The way I am thinking of this, this gets replaced by E mu A, E mu B, sorry, E A mu, E A mu, E B mu. Let me call this del A del B. Yeah. Flat space at the in the original action, of course, there is no difference between tangent space and flat space index. So this I have to replace by E A mu, E B mu, and then phi alpha, d mu phi mu, right? And now these d mu's have to be have the this omega, right? The term that I am ignoring is the fact that this d mu on d mu will also give a gamma mu euro. Okay, that term I am ignoring for now. Okay, because that I claim vanishes by itself. This order.
Because you're covariantizing only with respect to the soft factors, all deviations from flat space become factors of k.
Exactly. That's right.
So the more you go away from flat space kind of formulas, the more powers.
Exactly. That's right. K is the most of the software. Yeah, these derivatives which are acting on the soft factor, they are bringing up factors of k. Okay. So this is necessary for the first subleading corrections. And if you are interested in leading correction, you could have ignored this.
So if you went to the subleading, for instance, then you have to take the Christoffels also here, right? Because
Yes.
there's an additional factor of k
Yeah.
coming from that.
See, Christoffel of course also has a, I mean, at the face value, right? The Christoffel has also just one part of k, right?
Yeah.
So Christoffel and omega are of the same order,
Yeah.
right? It just so happens that the Christoffel cancels to this order. Okay, this I am not shown. This I am claiming that it cancels.
I see.
Okay,
It's not obvious.
it's not obvious from here. It's not
okay.
because at this order, Christoffel has a power of k. This also has a power of k. Okay. It's just that I am claiming that at the end, the Christoffel terms cancel to this order. Is this okay? And using this, we can now determine the coupling of the soft graviton to the rest of the fields. Okay, so this is the action. Okay, this is exactly the same thing that I wrote. I just picked up this part. Okay, because this was the original quadratic action. So this is the coupling of the soft graviton to the rest of the fields. And from this we can work out this vortex that you need to calculate. Right? So the gamma 3, let me go back to the diagram that you are trying to calculate. This one. This is a 3-point function. So this gamma 3, this is what we are trying to calculate. Right? So this 3-point function is basically laid out from this action. The only difference between here and here is that you have to symmetrize. See, this is no longer symmetric under the exchange of alpha q1 with beta q2. Right? Original k alpha beta was symmetric, but the way we treated this, I broke that symmetry because I put all the derivatives on this, the second one, right? So now to extract the vortex from here, you have to again symmetrize under the exchange of alpha q1 and beta q2, right? And that's what this is telling us. Here there are 2 terms, here there are, you can say, 4 terms, 1, 2, 3, 4. Is this okay? So now we are ready to calculate, right? So gamma 3 I wave, this is the coupling of the soft graviton field to the rest. So you have to take epsilon I alpha, gamma 3 alpha beta, then this is the propagator to k inverse because k was the 2-part function, right? The original quadratic action, yeah, this was the quadratic action. So the propagator is k inverse. Okay, again because I am taking all the fields, right? K inverse is a full propagator. Okay, in string theory, for example, once you start including quantum corrections, every field mixes with every other field. Okay, so you basically have to invert this big matrix. K inverse is that big matrix. And then this is gamma delta I. Okay, that's this piece. That's this piece. Okay, that I am just putting it in. So the result is that now everything has been expressed in terms of this k, right? Because k was the 2-point function, gamma 3 is now fully determined in terms of k, as you can see. And after this is basically algebra. Okay, you have to do the algebra and you can see what the various cancellations and what you get. So this is the second claim, that using this on-shell condition. Okay, so now to go from here to this step that I have given here, you have to use this on-shell condition that epsilon I alpha, k alpha beta minus pi equal to 0. See, this is a kinetic operator, right? So the general on-shell condition is that the external polarization should be annihilated by the kinetic operator. Okay? This is the momentum version of the position space on-shell condition. So using this, we can reduce that to this form. Okay, basically all dependence on k goes away. Okay, maybe if, I can try to outline this.
You reduce what to that form, please?
This one. I take this one, gamma 3.
Yeah.
So everything now depends on k, right? Basically, because gamma 3 has been expressed in terms of this 2-point function.
Right.
So basically, you after this you just have to do some algebra. Okay? And at the end you find that all the k's and k inverses cancel, everything else cancels, and it reduces to something which is totally independent.
This is to what order?
To every order, to first order in soft graviton, right? You have expanded to order k, right? But k alpha beta is the full 2-point function, right? I have not made any assumption about k alpha beta.
This was intuitively expected. You expected this?
Well, this was, I mean, in 4 dimensions, for example, people had given some general soft graviton theorem for massless states, right? There, of course, you use some specific k, right? Because you work with a specific action,
Right.
and there you find a structure like this.
I'm not able. You're doing the expansion in K, right? In a
No,
sense-
expand in small k. Yes, small k.
And so
Momentum.
the K which disappears is the small k.
No, the K which disappears is the capital K. This curly.
Oh,
That's the
Oh, sorry,
That's right.
okay,
Yeah,
that was another.
yeah. This is the
Okay.
this
Okay.
2-point function.
That your point is that disappears.
That is
the intermediate 2-point function. Oh, the whole thing.
the whole thing. I mean, see the point is, if you go back to this diagram, right? These are the 3-point function,
Yeah, which was
and these are the full 2-point function. Right? This propagator is K inverse.
Yeah.
Right? This 3-point function was determined in terms of the 2-point function, right? K, by using this covariant relation.
Right.
Now you have to combine this with this,
Right.
right? And what you find is that after you have combined, right, what the original 2-point function was disappears completely.
So it means it doesn't matter whether the soft graviton is attached to a graviton or to a scalar field or
Yeah, well, it matters only in this J. Okay, it matters in the way it couples to the spin that it carries, spin of the external state.
I see. Just to understand that intuitively, I mean, I would imagine that a soft graviton couples to a graviton very differently from the way it couples to a
Scalar.
secondary coupled scalar.
Yeah.
So how come that coupling constant dependence, if you did it more traditionally?
Well, see, coupling constant of course is universal, right? Because you get it by covariant relation,
Right.
right? It always couples to energy,
Right.
right? Whether the scalar and
Nice.
graviton carrying the same energy, you have same coupling, right? To leading order.
Right.
That's why. So now Sandeep was asking about the leading contribution, right? We can see the leading contribution also here.
Yeah.
See, this part has that pole. Right? This is the leading contribution, and somehow this you can see that the graviton polarization is attached to the energy momentum density of the particle. These are the subleading contributions.
The spin enters in the subject.
Yeah, the spin enters in the subleading contribution.
And the spin entering, can you so you interpret that first term as just the soft graviton coupling to the stress tensor.
Well, okay. I mean, let me add this and
Yes.
write the answer. Okay, if we add the two, okay, these are the contributions from subleading diagram, right? This is what you get out of leading diagram. So this is the form that you get. And so now, I mean, the point people normally interpret this as the orbital part of the angular momentum. Okay, it's like del P is like x, right? Okay, so this is like the orbital part of the angular momentum, and this is the spin part of the angular momentum. And I mean, this is supposed to be related to superrotation, but that I think you can ask Alok. What is related to what is called superrotation?
Super rotation.
But just locally, if you think of the soft graviton coupling to something, you're saying apart from this PIP, P mu, it also couples to something.
That's right, the first derivative. See, in some sense, physically you can think of it in the following way, that when you have taken external graviton, right, we know that a metric can be made locally flat to up to first derivative order. Right? You can make the metric to be constant and the first derivative values, right? So somehow there should be some general result that involves coupling of the metric to first derivative. And that's what the soft graviton theorem is telling us, that the coupling of the metric to first derivative level is universal.
And by universal, you mean it doesn't depend on what particle or what coupling.
Or what action you had and so on. Yeah, exactly. Okay, this is true for all massive states, obviously, right? I mean, the original formulation of how it comes from the asymptotic symmetries, right? That was of course specific to 4 dimensions, and also I think these require massless particles. But I think Alok has a way of understanding it also for massive particles, right? On how the asymptotic symmetries could give this. Okay, but I think beyond 4 dimensions so far nobody has tried to relate this to any asymptotic symmetry as far as I know, right? So this is the subleading soft graviton theorem. Yes.
So in the second line,
Second line, yes.
Which term came from the subleading diagram and which term came from the leading diagram?
Yeah, okay. So in the this is of course leading diagram. Here you can see the subleading term didn't have the pole, right? Here you got K inverse, So if you look at this second term here, with contracted with the K rho, you have a Pi dot K. Can you see that the third line, right, the contraction of the second term of the third line with the K gives Pi dot K. That's the one which came from the subleading diagram.
Okay. So there's one term which does not have the pole. Is that,
Yes.
that term
That's the second term of the third line contracted with the rest. That doesn't have the pole. That is the one which came from the subleading diagram. Everything else came from the leading diagram. And now we can go back to the problem that I had mentioned earlier, right? So suppose you add some quantity to gamma alpha which is off shell, which is proportional to pi square plus mi square, right? Then you can easily see that del del pi nu gives something proportional to pi nu, right? And this gives you pi nu. And they just cancel after you take the contraction, right? They cancel. So this is insensitive to off shell continuation, this formula.
So this formula, of course, you can check for various tree level Lagrangians.
Exactly, yeah. In fact, in 4 dimensions, people have done lots of tree level Lagrangian calculations, and this formula is.
So this formula was expected.
Yeah, exactly.
But you just got it in some way.
Yeah.
4 dimensions, I thought you have to go to
Tree level.
5.
Tree level. 4 dimension tree level, yeah. Yeah.
Okay.
So just to go to this BMS kind of story. So the first line of the right hand side. So there I can think of this coming from just the constant. I mean, if I'm thinking of some kind of
Constant graviton.
yeah, constant graviton stuff, and then the next thing is to have linear, in which the gauge transformation has a linear part.
Yeah.
And the linear part gives rise to both the second and the third lines. Because, no, sorry, I don't know about the intrinsic spin guy, but the orbital at least I can see that it comes from
Sure. But except that I don't know how to do it that way. In fact, I tried it. I think Alok also have tried it that way. That you take the metric back down, right, and try to find a coordinate transformation which makes it locally flat. Such coordinate transformation exists, right?
Yeah. So
But it's linear. See, you change x by term that is linear in x.
yeah, yeah.
And it's difficult to translate those in the momentum space.
Oh,
Okay, so it's
nice.
Sorry, Ashok, stupid questions, but the part of your analysis was just determining the effective three-point coupling.
that's right.
Between the graviton and this propagator.
Yes.
And that was sort of local with this propagator, meaning it just depended on the momentum going through this propagator.
That's right, yes.
And then there was another part, like the first part and then part of the second part, I suppose, that also cared about the other block.
Well, see the part of the second part that cared about the other one,
Yeah, that's what I was.
who is not very sensitive. See, it came because of this. You can see the del del pi rho, right?
Yes.
It acts on gamma alpha, right? That is the only part which cares about what is inside. And the reason that it comes is because, see, you have this is structure, right?
Yes.
This whole thing has a 1 over starts its leading behavior as 1 over pi dot k.
Yes.
So to get all the terms to the first subleading product, you have to expand this in Taylor series. So you have k rho del del pi rho of this.
Oh. It's just a little extra momentum goes
Exactly.
into that.
A little extra momentum goes into that.
That was the only effect.
Exactly. That was only effect.
I see.
But that effect was necessary because that's what combined with the other one
Ah.
to give a gauge invariant.
The first part was genuinely about that other block.
Exactly. That's right. The first part, I mean everything other than, so if you look at this diagram, these two are genuinely about coupling to that block.
Yeah.
Right? The terms that involve momentum derivative, right? One of them came from the subleading diagram.
Nice.
The other one came by expanding this other block in a Taylor series expansion.
Okay, good. So if I were just to summarize, I would say that firstly you have this clever way of determining the three-point coupling.
Yeah.
Then you just use this coordinate chain kind of idea to understand how the blob itself changes.
So yeah, I mean that's what went into determining the three-point coupling.
Yes.
right? That you covariantize to determine the 3 point.
That went into the 3 point, but also went into the other diagram.
And other diagram, yes, exactly.
Into the first part, yes.
First part, yes.
And then there's also the effect that when you do this 3-point function changing, you have to couple with the fact that a little extra momentum goes into that.
That's right. So you have to expand exactly.
So these three factors
Exactly.
added up give you your.
Exactly.
Yeah.
For the leading part, it is, just to understand, the leading part is, can we just say that we get it by, in a carefully defined way by thinking of the amplitude without the soft graviton, but in a metric which is shifted by some constant pieces?
Leading part.
Yeah.
In some sense, yes. I mean, if you shift the metric by eta mu nu, right? Or some epsilon mu nu, it should couple to the energy momentum.
Yeah, that's
That's what I think roughly explained. You can see pi nu you can think of the energy momentum tensor of the particle that is coming in.
right. And then part of the subleading is the also a change because the external states carry spin and that happens, but then there's more to it.
That's it, yeah.
So the 3-point function coupling, then somebody cares about this way.
Yeah.
Should I have known this that a very soft graviton? Sorry, I've asked you this before. But that a very soft graviton, if I couple it to first subleading order, that it cares about the spin. This is something that's intuitively obvious.
If you think in terms of particle, right?
Yes.
It may be possible to argue because it's like when you have to couple a particle with spin to external graviton, right? So somehow inside the covariant derivative, you have to introduce a spin connection. If you just covariantize, you get that energy momentum tensor, right?
Right.
But somehow it also couples to the derivative of the graviton is coupling to the spin. That must be coming from some spin connection.
Right. Right.
Right? But again, I don't know how to get it fully. I mean, from this. But I think that's the intuitive understanding of why.
And it also comes, sorry, but it also comes, you said, to the orbital part of.
Yeah, that's this one. Right? Orbital part is basically the derivatives with respect to the momentum.
And so just to understand that in terms of the 3-point function, the 3-point function couples to the orbital angular momentum.
See, people refer to as orbital, but I'm not sure that this is really orbital angular momentum. Maybe Alok has some idea. Is this really angular momentum of something? For the particle?
Yeah, I mean, if you have just scalar field, the subleading subgraviton theorem for scalar field, then the last line will be absent.
That's right.
There is no intrinsic.
Yeah.
So that would be just.
So this term is there.
Yeah.
Right? But can you think of this as this angular momentum of the scalar field around what? I mean, that's,
Yeah, I mean, from the symmetry perspective, it's actually clear. In the sense that if you take just the usual Lorentz boost, and then you will just get basically this term written for Lorentz boost, you will just get the angular momentum of the scalar particles viewed at infinity, measured at infinity.
I see. So from BMS perspective, you are saying that
Yeah,
this
if you
angular
take
momentum.
not arbitrary BMS rotations, but just a Lorentz boost,
I see.
then this term reduces to this.
I see. Yeah, but in Feynman diagrams, I'm not sure exactly. It's a scattering, one of which is a scalar field, right? And it's angular momentum carried relative to the rest of the fields somehow. Maybe that's center of mass, yeah.
Maybe in the frame in which it's at rest,
Yeah,
then it doesn't care where you.
yeah, that's true. Yeah.
So I could just do this by semi-class. I mean, is this just a semi-classical statement about gravity that gravity is coupled to some?
Yeah, so this part I think is semi-classical, that's the leading theorem. For the subleading one has to be, it may be possible to give a semi-classical derivation, right? Given that it's universal.
Right.
Just think of a particle scattering, right? Just think of a particle scattering, right? And you put it in a background. So soft graviton means what? That you are trying to scatter it. The original particle scattering was there, now you are trying to see how it gets deformed if you have a very slowly varying gravitational field, right? That's what you are trying to determine, locally slowly varying gravitational field. Right?
So from, I got it, yeah.
Yeah, but what I was saying is, suppose I've got a solution of gravity. then I take the metric and change that a little bit. And I want to know how that's coupling to the solution.
Yeah.
It's some very
Yeah.
universal statement.
Yeah. Yeah. Take a solution that represents this scattering.
Yes.
Since you are using 1 pi, you can think of this as a classical solution of the 1 pi effective action. Right? And then see how it changes in the present of
But I was wondering if it was even more general than a solution that represents scattering. Because you've got something that's saying that it couples to a stress tensor plus angular momentum.
Yeah.
So it might be just a very general property of solution.
Yes.
I mean, sorry, but when I tried to suggest that earlier, Ashok correctly pointed out that his theorem is more general because the stress tensor way would have worked if you didn't have any gravity, if you didn't have gravity in your system.
Yeah, but that I think, once you split into soft and the finite energy part, right? Even gravitons gravitate, right? That's what you are using. That
Gravitons gravitate, but
you can study the propagation of a fast-moving graviton in a slowly varying gravitational field.
Yeah. You don't want the local stress tensor. You just want the energy. And that's well defined. And you don't want the local angular momentum because the big soft graviton is so huge. It goes over all space. Isn't that right?
Yeah, I think that's.
Yeah. And that's
But
why
since you are doing an expansion in soft momentum, right? You are really the leading term is really sensitive to total energy of the system.
It's like a multiple expansion of T mu nu as a power series in K. Isn't it right? I mean, the homogeneous part of T mu nu
Could be, yeah.
is the first guy, and then is some.
Well, I don't know if it's just T mu nu because
No, sorry, T mu nu is not the right thing. It's okay.
meaning it's the coupling of the gravity, right? So somehow if you are coupling a particle to gravity, right? The leading part we all know it's given by energy quantum tensor, right?
Yeah.
But I think the first coupling to the first derivative of the metric should also be universal because it should be given by covariant addition of the
right.
free equation, right?
Right.
And that's what this is saying. It's in the usual way of covariantizing, we don't see the spin part, but somehow it must be there.
Does a gyroscope couple like this? Should I find this formula in Visnathon Vila?
Yeah, possibly. Yeah.
So maybe this everyone knowing BMS and all this, but so if it's the total energy in the presence of gravitons, then it's the ADM energy, which is the first term.
Yeah, probably the first pi mu, you can think of the ADM energy of all the particles.
Or everything.
Actually, I do think the gyroscope does couple like this.
It does couple like this?
Yeah.
You've taught it in a course, Loga.
What? Sorry?
Siraj is asking if you have taught it in a course.
So I think this is probably you can relate it to this post-Newtonian expansion of how a spinning particle moves in a.
That's exactly what I was wondering. Yeah. Yeah.
So kind of things that people talk about. This. Yeah.
We have some slides showing part of the proof of these two claims, but it's, that's why it's an appendix. So, if you believe those two claims, then you don't have to go through this.
If you are, whatever you think, we have time.
Okay, I can show you how. Yes. At least the gamma, how it disappears, right? Because it appears in the same order. Yeah, so this will also probably illustrate how you can go beyond. Okay, because that's what we are trying to do now to do the subleading order. There you have to go one order beyond. So take this quadratic action, and what I said is that every time you have a pair of terms, del mu, covariant guys, right? It will be d mu, d mu. Okay, doesn't matter which order you are in. You should get a gamma rho mu nu del rho. Okay, that's the effect. So now you have to translate it to what it means in the momentum space, right? What kind of coupling it generates to the soft graviton. So this is what it is. Because we are removing two momentum factors, we have to take and replace it by gamma rho mu nu, okay, in the momentum space. It's clear, otherwise the formula is similar. So now we have to analyze the effect of this, right? And the idea is to show that this actually vanishes to the first order equation. Okay, so this is the proof. So we start with this. Here I have given the explicit expression for gamma, although you will not need it. Okay, just to show that it has one part of the soft momentum. Now we use this k alpha beta of q to q equal to k beta alpha minus q. That was because the original two-point function was taken to be in a symmetric form. In this context, q2 is equal to minus q1 minus k, so I replace it by q1 plus k and substitute. And so this is what we get. All I have done is that I have replaced here q2 in terms of q1 plus k, use this identity. And this q2 row I have replaced by minus q1 minus k because of this delta function. Now in this I can rename variables, just exchange q1 and q2 and alpha and beta. Okay, just rename variables. So it becomes d2q1, d2q2, this of course remains the same. This becomes phi beta q2, and I am expanding to, see there is already order k term. So everything else I can expand to the leading order, right? So basically set k equal to 0 in the rest of the expressions. So this is what one gets by doing this. And now the thing to notice that this is exactly the negative of what it was. Okay? There is phi alpha q1 here, phi alpha q1, phi beta q2, phi beta q2. That the only difference is there is q2 row here and there is a minus q2. And effectively it's happening because we are replacing two derivatives by one. Right? That's the role of this gamma, right? d mu factor we are replacing by one derivative, and that ensures that once you impose this symmetry, because the two derivative term was symmetric, the one derivative term becomes antisymmetric and that vanishes. To next order of course it will contribute, but to this order it vanishes.
So, Ashok?
Yes.
If phi was the fermionic field, then you will have some extra minus over x factor with it.
Yeah, so if phi was a fermionic field, then there are two minus signs. One is that there will be minus sign in this relation. Right? K alpha beta q2 will be minus k beta alpha minus q2. And there will be an extra minus sign because you have to exchange the order of these two. Right? If you compare the one in the top line, right? Here it's phi alpha phi beta, here it's phi beta phi alpha. So those two minus signs basically cancel. Okay, so effectively this minus q2 is still there. So this is the reason why the gamma factor vanishes.
Could I ask, if you went to one higher order,
Yes.
then the first part seems pretty unclear. How would that first part of your proof generalize?
Okay. So this is still work in progress with all of them. Yeah. So basically the first part, the gamma tilde part, right?
Yeah.
So what we will do in the gamma tilde part is basically you have to do the analog of this. We have to keep the not only change effect of shift of the metric, but all derivatives are replaced by covariant derivatives and analyze that. So the idea is that we think of this first part as some function of q1 up to pn carrying alpha 1 to alpha in index, phi alpha 1 p1 up to phi alpha in pn, and then the delta function delta d some pi. There is an integral, right? d p1 to dpn. So the idea is that this effectively means various derivatives acting on all these fields. Right? So each of these pi's now we have to replace by this kind of tree. Okay. And now we also have to keep the Christopher symbol. That doesn't cancel anymore.
Nice. So, but it sounds like you're saying that this is a systematic procedure that you can take to any order.
No, see, to next order. So here, okay, let me say what we expect is going to happen.
Yes.
Okay. That is in the first, the subleading order.
Yes.
this gamma tilde analysis will be universal to this order. Sorry, that's gamma tilde. Yeah. This analysis, because you can still determine the coupling by covariantization. Right? No Riemann tensor.
Oh, it's when the Riemann tensors come in.
Yeah. Once the Riemann tensor comes in, then of course you can determine this.
I see.
Okay. So this part is still universal.
I see.
Now in gamma, okay, of course it's not universal.
Right, because you need the Riemann tensor.
You need a Riemann tensor. Okay?
Yes.
But the Riemann tensor terms are very specific structure. That once you put the Riemann tensor here, you have already spent 2 factors of soft momentum.
Right.
Okay. Now you just pick the leading contributions from here.
Right.
Okay. So the Riemann tensor part, okay, gives a, first of all it gives a term proportional to the Riemann tensor involving the soft factor. Right.
Yes.
Epsilon and k have to appear in the linearized Riemann tensor combination. Okay. And furthermore, it has no derivatives acting on this piece. Right. Right. So it's a multiplicative factor. Right. Okay. So that's the general universal or the general structure of the subleading soft theorem
Will be that, but with some unknown.
will be there is a universal piece, okay, and then there is some unknown piece, right? But about the unknown piece, what we know is that it will involve the Riemann tensor involving the soft factor,
I see.
right? And it has no derivative
I see.
on the amplitude of the soft factor, right? This is a multiplicative factor involving the amplitude of the soft factor.
I see. And then you said that that can only be determined if you know the specific interactions.
Exactly. So that part can only be determined only if you know the specific interactions.
So it's a structural feature.
Exactly.
And then you go one higher order and everything.
Exactly.
And
But
then
the one part of higher order I can't see anything because now this diagram will start contributing with at the level of Riemann tensor, right?
And then since there are so many different external momenta, that goes totally out of it.
Exactly. And the only thing that you can say is that the coupling to soft graviton should be proportional to Riemann tensor.
Right.
That it will involve a factor of Riemann tensor and then some very complicated.
But it might even be different factors of Riemann tensors for different external P's.
Exactly. Yeah.
So it could be very complicated.
Yes.
Much harder.
Well, the what is the Riemann tensor of course is for the soft
It's
part.
universal. Yes, I
That's
agree.
universal, right?
But I'm saying the coefficient could be different for different
Exactly.
P's.
Certainly. Yeah. Yeah.
Yeah.
So Ashok,
Yes.
in the subleading term,
Yes.
the coefficient that multiplies the soft Riemann
Yes.
should be basically like should be like delta L by delta R, right? It's like the term which appears in the Wald formula.
Which appears in the Wald formula. I see. I haven't thought about it that way. It delta L by delta R. Probably yes. Okay. Except that. Yeah. See, what I said is that there are some Riemann tensors which come because of this change in gauge fixing condition, right? I think that okay, that can be kept track of presumably. That if you use, for example, this harmonic gauge, right? You start with del mu h mu nu times del rho h rho nu, right? That's the combination you start with. Then you have to integrate by parts because you want to cancel some part of the Einstein-Hilbert action. Okay? You integrate by parts, and in flat space, of course, it cancels by itself. In the card space, there is a Riemann tensor piece which is left over. That part you don't see from Wald, right? But of course, those parts can be kept track of in principle. So it's possible that after you have kept track of those, then the unknown part will involve the Wald part. Yes, that is true. Because the unknown part should involve the derivative of the Lagrangian with respect to the R mu rho sigma. Right? Because that tells you how the soft part comes to the rest of the piece. Yes.
Okay.
And suppose you were to try to generalize this to soft photon theorem.
Yes.
So how much of it would go?
The leading soft photon is universal,
Clear.
right?
But there's no subleading universal.
Well, the subleading is not universal because
Oh, it's not.
soft photons coupled with F mu. See, you can consider the G minus 2 coupling, right? F mu can couple to this. So, first derivative order it already becomes non-universal, but you can still identify universal P's, right? By exactly the same trick, right? So, subleading graviton and subleading photons are on the same level.
The trick being that it will couple to F mu nu
Exactly.
of the soft photon.
Yeah. It will couple to F mu of the soft photon on the external line.
Yeah. And so it's basically the difference is that the 3-point coupling. But the 3-point coupling is less universal for electromagnetic
in the classical language, right? I think it's just the fact that metric can be
Two derivatives.
yeah, up to 2 derivatives it can be made flat. Right?
Yeah.
For gauge, it's up to 1 derivative it can be made flat. Right?
Yeah. The first
Derivative you cannot remove.
yeah.
Right? That's like your field strength.
The first gauge covariant thing in gravity is two derivative. The first gauge covariant thing in
Electromagnetic is
one
1
derivative.
derivative. Exactly.
Yeah.
This sounds very similar to anomalies. You know, like you can find some universal part of the effective action by integrating anomalies, but whatever is gauging value, you have no idea about that.
That's true.
So it almost feels like that in the k going to zero limit, some differential equation of that structure is appearing, whose
Yeah, the gauge invariant piece you cannot determine, but anything else you can determine.
yeah.
Yeah.
So the
Yeah, I mean you can say, I don't know whether you could call it anomaly, but at least these parts, the parts which you can determine, right, are not manifestly, do not display manifest covariance. In the sense that they are not, the k mu and epsilon mu are not appearing in the combination of the contents. So in that sense, I think it is true that these are not manifestly gauge invariants, and that's the reason why their structure is completely fixed.
Any more questions? Loga?